So I think that it's okay. We can start.
Yes.
Okay.
So hello everybody. The talk of today deals with interval observer design for uncertain discrete time linear switched systems with unknown inputs. And the speaker is Ghassen Marouani. Ghassen is a PhD student. He obtained his engineering degree and his master degree in electric engineering and in automatic control in Tunisia. And currently he's preparing a PhD also in Tunisia. His research interests focus on interval observers, fault detection, and fault-tolerant control for switched systems. So Ghassen, you can start your presentation, please.
Thank you, Tarek, for this presentation. It's a pleasure to be among you to present this theme. So the outline of this presentation. So I will begin with an introduction where I will introduce switched system and interval observers. Then the problem formulation. Then I will present the two approaches to design the interval observers. So a classical approach based on decoupling the unknown input from the state vector. And the second approach is based on the TNL method to prove the effectiveness of this of the two approach. A numerical example will be presented, and I will finish with the conclusion. So, switched system represent a class of hybrid systems which are composed of finite number of continuous subsystems where a logical rule operates switched between systems. So several physical systems can be modeled by a switched system. We can say power and electronic system, automated highway systems, and flight control system, network control system. Now let's focus on interval observers. The problem of state vector estimation is very challenging and can be encountered in many applications. Several cases are encountered which we can say models without uncertainties, model with certain parameters, and model with uncertain parameters, and in the presence of unknown inputs. So several solutions can be presented. We can see adaptive approach, robust approach, and set membership estimation and interval observers. So we will focus on interval observers. So to address this theme, we give the described system. So the dynamical system given by equation 2 is an interval of observers if the two condition are the condition 3 is satisfied. So an interval observers allow to compute the set of admissible values and provide the lower and upper bound of the state vectors. So to design an interval observer, two properties have to be verified. So the first property is the non-negativity of the upper and the lower bound of the state vector, and we have to ensure the stability of the estimation errors. So now let's focus on the design of interval observer for switched discrete time system in the presence of the unknown input. We have the following switched system where the X is the state, U is the input, Y is the output, omega is the disturbances, V is the measurement noises, and D is the unknown input. The objective is to design an interval observer. This choice because such kind of observers allow to cope with such several type of uncertainty, and allow to join. We have to join estimation of the state and the unknown input, verifying the equation 5, where the state vector is encountered by two bounds, and the same case for the unknown input. So we will introduce two approaches. The first approach is a classical, based on decoupling the unknown input from the state vector. This approach is characterized by the presence of the two changes of coordinates are used. The first time we have to estimate the bounds of the state vector, and then we have to count the two bounds of the unknown input vector. The second approach is can be called TNL method. This method allows to the estimation of the state vector and the unknown input simultaneously. So it's this approach is a new structure for providing more degree of freedom and allow to relax the design condition of the classical approach. To deal with these two approaches, some classical assumptions are introduced. These assumptions are usually used in the design of interval observers. The analysis of stability is based on the use of the following lemma. So we will use principally a multiple Lyapunov function to discuss the stability of the estimation error as explained above. So for the classical approach, first change of coordinates where z equal t sigma q x given by this change of coordinate. So the switched system have the following form, where the matrices T is given as below. The matrices A tilde, B tilde, and C tilde, D tilde are explained a function of the matrices T sigma Q. So we get two after this change of coordinates, we get two change of two subsystem. The first subsystem is a non-input-free subsystem. We can remark that the state vector, the absence of the unknown input in the state vector. And the second subsystem is a non-input dependent system. To have these two subsystems, we have the Y tilde, U tilde, and U sigma Q. So let's focus on the unknown free subsystem, which can be written as so to design an interval observer for this system, two properties have to be satisfied. The first is the Framer property, which is the notion of providing intervals in which the state variable stay, and the second property is the stability property, which cares of the length of the estimated intervals. So we have to determine the gain of observer such the A tilde indexed by 1 sigma q minus L sigma q are non-negative, and the estimation error are stable. So the existence as a solution in literature, usually non-singular transformation is used to guarantee that the P these matrices are non-negative. but the existence of the common transformation P for all modes of the switch system is not obviously ever impossible. So the design, so we propose two conventional observer in the original, which are given by the following equation. So to guarantee the positivity or the framer, the condition of the existence of the framer designs are given in the following theorem, where P sigma Q are a non-singular transformation such that those matrices are non-negative. And the bounds of the substate vector Z are given by the following equation, satisfying the 11 inclusion given by this equation. The stability condition or the condition of existence of the interval observer, or such the framer become an interval observer, are given in the following theorem. We have proved this term using the lemma of the ESS lemma to prove the stability of this kind of switched system. So by satisfying those conditions, the lower and the upper observer orders are ESS, and the framer given by the following equation are an interval observer. In addition, the gain of the observer is given by this equation. So now, after we have determined the interval observer for the independent unknown input-free subsystem, the bounds of the state vector X are deduced in the following theorem. With different components of the vector X are given as explained in this theorem. Now we have now to determine the expression of the unknown input in function of the Z2. We have as a result this equation. And now the upper bound and the lower bound of the input vector D is given as explained in this equation. We introduce the variable xi, which are minus VQ, where this xi are the upper bound and lower bound of xi q are respectively given by this equation. So we are able now to estimate either the state vector and the unknown input of using the classical approach based on two change of coordinates and where the estimation is first of all where we have to estimate first of all the unknown the state vector, and then after we have the result of the estimation the vector, we can estimate the upper and the lower bound of the unknown input. So this method present some difficulties. Essentially, the difficulty came from the two change of coordinated. So we introduce a new approach to design an interval observer based in presence of unknown input. This new method is based on TNL method. So this methods is take place by augmenting unknown input as a part of the state vector X tilde. The structural condition for decoupling unknown input is often used in the literature. So the switched system take the following form, where X tilde, where the different component of the switched system are given as and different matrices are explained as X tilde is x q plus 1 and the unknown input vector. The E sigma q are explained is a matrix. The matrices are given as A tilde and B tilde, also C tilde. So the goal is to design an interval observer for the augmented state vector x tilde k plus 1 plus 1. We have to determine the underline x tilde q and the overline x tilde, such that respect this inclusion. So we propose as Framer candidate the following structure. We can remark and these structures we introduced the new matrices T and N. T and N. So T and N will provide more degree of freedom in the design approach. Those matrices are computed such as this. The following equation I have to be verified. So to design an interval observer, as mentioned below, we have to verify the negativity condition, which is provided using the following theorem. Some element of proof of this theorem. So we have to introduce the two vector of estimation error, the overline vector and the underline vector. Then we have to calculate the dynamic of for the upper error. We calculate the dynamic of this vector. So we have this expression. So from the fact that the upper error at Q0 is greater than 0, it follows that for all Q the upper error is positive, and the same reason prove that the under error is greater than 0. To discuss the stability condition of this framer, let's define an estimation error given as overline the overline of the error vector minus the underline of vector error. The dynamic of this estimation error is given as explained in the question. So the condition the necessary condition of the stability of the framer is explained in the following theorem in terms of LMI. So by satisfying this condition, the proposed frames become an interval observer for the switched system, and the optimal gain matrix are given as to prove the effectiveness of the two methods. We propose the switched system with the 3 modes, where different parameters of the switch system are given as the uncertainties and the noise measurement are bounded by the upper and lower bounds, and the unknown input is given as we get as a result of the simulation of the effectiveness of the two methods. We have 2 interval observer, but we can see that the results given using the TNL method is better than the one where we used a classical approach. And for the unknown input vector, we have the same results, and the results using the TNL methods is better than the one where we use a classical approach. As a conclusion, in this presentation, we have presented two methods to design interval observer for switched system in presence of a known input. Sufficient condition of the stability of the interval observers are derived in terms of LMI. The effectiveness of the proposed approach are shown on a numerical example. And thank you for your attention. Thank you.
Thank you, Ghassen. Thank you very much. So we have time for questions. Would like to start?
Okay, maybe let me start with there's a couple of questions, 2 or 3 questions that I have. When we go to the slide, just the slide number 33 that you had shown at the end, where we have seen the simulation results for estimating this unknown input. On one of the previous slides, you had written that the initial condition for the unknown input is equal to 0. And here on this slide, it looks like some interval at the initial point of time, k equal to 0. Is this? Can you explain this a little bit? I think it was on the slide 24 where you had introduced
24.
the initial condition for the yes, the unknown input d. Yes, here in the lower part in the theorem, you had written that the augmented state is initialized with a 0.
Yes.
And
yes.
your diagram looks a little bit different. Can you explain this?
Yes, it's true. I think you are reason.
It's because I assume you have to at least perform some intelligent guessing of non-zero interval bounds at the beginning, such that the true disturbance at k equal to 0 is included.
Yes, I think.
Okay, and my second question was on the transition between the slide 28 and 29.
Yes.
Yes, on 28, you had this matrix P. This was the matrix with which you have proven the stability in your Lyapunov function approach, I think, as a matrix depending on the discrete state of your hybrid system. That depends on the switching parameter sigma. And on the next slide, you have a matrix P that doesn't carry this index in equation 45.
Yes, you have a reason. It's a fault of inattention. I have not made attention in to write this expression, but the right expression that the matrix P depends on the sigma Q.
Okay,
right.
that means you always have
yes, because
say some mode dependent Lyapunov functions.
Yes, because the stability analysis I have used a multiple Lyapunov function based on the lemma which I introduced in the beginning of the presentation. So it's you are right, and I have to change P to be depend on sigma Q. But the paper, the different paper which have been published, the gains depends on matrix P, which depends on sigma Q.
Okay.
It's a typo here.
Yes, it's just a typo because I was just wondering here if, let's say, there's any reason how to simplify this to a, let's say, commonly Lyapunov function here. Yes, and one further question that I have, and I think that's more or less a philosophical one. If you go to the slide 23. The way how you augmented your state vector. Yes. 23. Yes. it was, yes, I think you have some overlay mode here. Maybe one in advance where you define the matrix E, the capital E matrix. Here, yes.
Yeah.
It was 22, okay. This matrix capital E looks like that you are defining this augmented system model in such a way that you're including the disturbance in the updated state. That means in this x tilde k plus 1. And it's not included in the matrix A tilde. An alternative would be to introduce a zero block in the upper right part of the matrix E and a non-zero block in the upper right part of the matrix A tilde. Would this make a difference concerning, let's say, observability or solvability of your LMIs, or would this be equivalent?
So I think that I have an assumption that we have to introduce to guarantee the observability of the observability and the resolution of the LMI.
Yes, I think it's visible here that it is observable in the case, or observability can easily be shown if you introduce it in the matrix E.
E and C. Yeah?
Yes, yes, E and C, yes.
So we have to introduce some assumption on the matrices E and C to guarantee the observability and to have the resolution of the LMI.
Okay, and that's the reason why you introduce the disturbance in this updated state vector, in the vector at the time step k plus 1, and not in the old one.
Yes.
Okay.
Thank you.
Thank you.
Thank you.
Thank you, Andreas. Is there some questions, please? We have time for questions.
Yes, if there's no one else, I have a further question.
Yeah, of
course.
course.
What you presented today is, let's say, yes, a very nice comparison of these two different approaches for the discrete time scenario. Did you think of making a similar comparison for continuous time systems?
Very nice question.
Yes, it's just a question for an outlook. Or what do you think would the obstacles be for the continuous time?
For the classical approach, there is some results that focus in this topic, but where I used the augmented system, I don't know. I will try.
It's more complicated for the continuous time systems case for the augmentation technique, because you need the derivative of the unknown input, I think. So it's more a bit complicated.
Yes, what I could imagine for the continuous time case, you could do something like, let's say, you do not precisely know the derivative of the unknown input, but you know some kind of interval in which the unknown input is included. And then this may work, I think.
Yeah, of course. Yeah. It is possible, yes. Or we can also use some techniques based on numerical differentiation, for example, using sliding mode techniques.
Yes.
Maybe it's possible also to estimate the unknown input, but not exactly with this approach. I think that it's more complicated with this approach.
Yes, for the continuous case.
Yes, but I think it's not so big of a restriction here, because if you have a really linear continuous time system model that can exactly be discretized, for example, by calculating the matrix exponential, I think then it's working.
Yes, yeah. So thank you, Andreas. Are there some questions, please? think that there is no question.
Yes. Maybe it was absolutely perfectly clear what you presented.
Maybe. I hope so.
No, it was really a very nice talk. I just have one more comment as an outlook, which may also be interesting for your thesis. Currently, let's say this benchmark scenario that you had is a really very low dimensional system model. And maybe you could find some benchmark scenario, let's say, where you have let's say, a much higher dimensional system model, let's say 8, 9, 10 component state vector. And yes, also visualize the difference with, because I'm pretty sure that the novel approach will much more outperform the classical one in cases where your dimension of the state vector is much larger. Because then even the transformation that you had in a classical technique is more likely to become, let's say, even impossible.
I completely agree with you. So I think that there is no question. Maybe you can conclude, Andreas.
Yes, let's conclude for today. Many thanks again for your very nice presentation. Yes, also Victoria is writing here a nice talk. Many thanks. And yes, for me, it's just time to wish you now a nice Friday afternoon, weekend. And we're changing a little bit our schedule. The next meeting will be right away, Friday next week. And Friday next week, we'll have a talk of Bartolomei Kubica. And yes, until then, stay healthy and see you very soon.